cloud. All right. Hello, everybody. My name is Greg. Most of you probably know that already. Today we are here to celebrate the slightly early demo. One of our data science students, Tara, she has to go to college next week, so we wish her the best. But before that, she wants to share her project with us. As always, for every demo, I'm going to ask that all of you attending please refrain from unmuting yourselves or unmuting your video to the best of your ability. The less video there is, the easier, smoother the call is for those of us with worse internet. And audio feedback is just a frequent issue, so please limit it to just Tara until the designated Q&A time at the end, in which time will be obvious. She'll say it, and then you can unmute yourselves as necessary. If for whatever reason it gets too chaotic, which it has never done so far, I'll mute everybody and ask you guys to use the chat for questions, and then Tara can use that to respond instead. But without further ado, Tara, you can unmute yourself, start sharing your screen, and start with your project whenever. All right.
Sounds good. Okay. So, oops. This is my COVID-19 policy and mobility data science project. And in the presentation, I'll start with the question that I wanted to address. I'll explain the data and then show my visuals on the policy and mobility data. And then I'll get to the part where I predict mobility trends from policy data. And I'll talk about the challenges I faced in this project and possible next steps. And along the way, I'll explain all the algorithms and machine learning models that I used. So throughout the pandemic, people's mobility data has been important to lawmakers and business owners because analyzing mobility data helps these people predict the spread of COVID cases, determine the economic effects of COVID and lockdowns, and predict sales and the number of customers for a business. So in this project, I used US mobility data from over the course of the pandemic, as well as US data on COVID-related policies to answer the questions, how can US states be grouped by their COVID-19 policies and mobility trends? And can data on coronavirus policies be used to predict the average mobility of people in the US? So the policy data set I used was put together by Oxford's Blavatnik School of Government. And the four main policy indices that are used to explain different states' COVID-related policies are the Containment and Health Index, which measures each state's lockdown laws, testing policies, and other investments in healthcare. Then there's the Economic Support Index, which describes each state's level of economic support and debt relief for the people who live there. Then there's the Stringency Index, which is a measure of how strict each state's lockdown policies are. And there's the Overall Government Response Index, which is a measure of how strong or weak the response of the state government is overall the other indices together. So in this data set, there's a row for each of the 50 states in DC from January to the first week of September. The other data set I used was put together by Google, and they collected mobility data from people's phones from all over the world, but I only used their data for the US. And the way they measured mobility is the number of visitors in different places. For example, the number of visitors who go to a grocery store in a day. And the mobility is measured as the percent change from a baseline of the number of visitors in retail and recreation places, groceries and pharmacies, transit stations, workplaces, residential places, and parks. And the baseline numbers are the median value of visitors in each of these places from January 1st to February 6th, 2020, and they're adjusted by the day of the week. So in this data set, there's a row for each region of each of the 50 states in DC from February 15th to the beginning of September. And I've condensed the data in this image so that there's only one row per state per day. So now I'll talk about the visuals I made from the policy and mobility data. And first I'll talk about the algorithm I used to make these. So Kmeans is an algorithm that's useful for splitting a data set into a number K of clusters clustered by similar data points. And there are four main steps in this algorithm. So the centroids are the moving x's on the diagram, which will become the centers of each cluster. And in the first step, K centroids are randomly initialized. Then all the data points are iterated through and each point is assigned to the closest centroid. And by the end of this step, there are distinct clusters of points within the data. Then all the data points are averaged out in each cluster, and these averages are the new centroids. And those 3 steps are repeated until the clusters are pretty much set. So I did K-means on all of the policy data, and these are my results. So if you try doing K-means with different numbers of clusters, which is the number of K, you can plot the sum of squared distances of the points within each cluster against the number K, which is this graph on the left. And you pick the number, like the optimal number K, by choosing the elbow point, which is the point at which the graph bends. So here the elbow point was at K equals 4, which is why you see 4 different color clusters in the 2 graphs. So in the next 2 graphs, you can see that the points are split into those 4 clusters, with the axes being the economic support index, the containment health index, and the government response index. And the 4th index, which is the stringency index, is the size of the data points. So the larger the data point, the more stringent the policies are. And the middle graph is just the data from the month of April, where the graph on the right is data from March through September of the pandemic. And I'll show the actual graph. So you can see when you look at the top right cluster, which is the red one, some of the states in this one are Connecticut, New York, and Alaska. And these states have the strictest coronavirus policies with high economic support, high containment health index, high government response index, and very stringent laws. And on the other hand, there's the green points in the back, which is the states with the least strict coronavirus policies, which are, some of them are like Texas, Alabama, and North Dakota. Then there's the blue cluster in the middle, which has medium strict policies, and states in there are like Mississippi, Oklahoma, and Washington. And then the cluster on the right has states like Massachusetts, Illinois, and Hawaii. And these these states have high government response, containment health, and stringency indexes, but some of them don't have as high of economic support. So based on that graph, oops. Here are the states that are in each cluster based on their similar policies in response to the coronavirus. And some of these states we talked about, but we'll take a closer look in a few slides. So here's another algorithm I used to make the next graph called principal component analysis, also called PCA. And PCA reduces the dimensionality of a data set while trying to lose as little information as possible from the original data. And as you can see in the image, there's a 3D graph turned into a 2D graph. And you can see that PCA finds new axes that hold most of the variance in the data. And it does this by transforming the original features into new features called principal components. And each principal component includes information from multiple of the original features. So for the Google mobility data, I used principal component analysis to reduce down the number of dimensions from 6 to 4 so that it could be graphed and visualized easier. Then I did K-means to cluster the data, and conveniently the elbow point for this data was 4, just like it was with the policy data. So 4 clusters is the optimal number. And all the way to the right is all of the data for all the mobility data for all the states for the whole February through September, which is about 2 million data points, which is why the clusters are kind of layered, which is why you can't see them distinctly there. But then in the middle is slightly less data points with just the month of April. And on the axes are the first 3 principal components, and the 4th principal component is represented by the size of the data points. I also put down the greatest contributor to each principal component to put them into more context. So you can see that in the bottom right. And I'll show you the actual graph for April for this. From like an overhead view, you can more clearly see the 4 principal component, or the 4 clusters. All the way on the right in the green cluster are states like Connecticut, Texas, and Illinois. On the cluster on the left are states like DC, Hawaii, and Massachusetts. The blue cluster is states like New York and Minnesota, and the purple cluster are states like Montana and Wyoming. Um, and here are the states in each cluster. But more importantly, here's a comparison of the states in each cluster for the policy and mobility data. So all the states that are in colored font are the states that are in common in each cluster. And as you can see, there's some, but not a huge amount of overlap here, which indicates that policy and mobility trends don't always move exactly together. And that'll help explain some of the error in my neural network later. So next is the part where I use a neural network to predict the daily average mobility from policy data. And a neural network is a type of machine learning algorithm that finds relationships within the data and uses it to make predictions. And specifically in RNN, a recurrent neural network is a neural network best for time series data. So recurrent neural networks take in the data in a specific order and process it sequentially, kind of like you see in the diagram there. And in each cell, which is the green boxes, the recurrent neural network takes in new data and also the output from the previous step. And importantly, they remember information from the data it has seen before, and they learn relationships in the data, especially time relationships. So RNNs can be used to predict future data, which is what I did in my project, and they have no set size. So a specific type of RNN is called a long short-term memory network, or an LSTM, which is a special kind of recurrent neural network. And within each cell, they do extra operations on the data. And these extra operations allow it to remember or forget information that's passed to the cell, so that only the most important information is passed from cell to cell. And these extra properties that LSTMs have help the neural network more accurately make predictions. So for my neural network, I used an LSTM for multivariate time series forecasting, which basically means that each cell takes in information from multiple variables and it predicts the data for a certain point in time. So each cell in the LSTM takes in all of the policy indices from the day before. It takes in the average mobility from the day before. It takes in the cluster number, the policy cluster number, and the mobility cluster number from the day before for that state. And it takes in the policy and cluster data from the given day. So basically it takes in the policy, cluster, and mobility data from the day before and the policy and cluster data from the day of, and then it predicts the mobility for that day. So I reformatted my data frame to more clearly show the inputs and outputs of each cell, and there's a row for each state for each day since March 1st. The first 13 columns of the data frame are the policy and cluster data and the mobility data from the day before. And the very last column is the average mobility on the given day, and that's what my neural network is predicting. And I trained my neural network on the data for the first 29 or 30 days of each month, depending on how long the month is. And I evaluated my neural network on the data from the very last day of each month for each state. So in a neural network, hyperparameters are like properties of the model which are set by the programmer when creating the model, and they control how the model learns. So I tuned the hyperparameters of my neural network in Google Colab, where I could run about 4,000 different models with different hyperparameters and choose the one with the lowest error. So I created a for loop with 6 for loops nested within one another, and each for loop iterates over possible values for the hyperparameters so that the model, which is built in the body of the giant for loop, can be tried out with different combinations of hyperparameters. So the first hyperparameter I tuned for this for loop is the number of LSTM units per cell. And if you remember the picture of the LSTM cell a few slides ago, each LSTM unit does the LSTM specific operations on the data. I also tuned the size of each of my 3 fully connected layers, which are the layers of neurons that connect to the LSTM layer, and each neuron in these layers also does operations on the data. Then I tuned the number of batches, which is the number of data points that are passed into the network before the network calculates how far off its predictions are from the true values. And lastly, I tuned the number of epochs, which is the number of times the network goes through the entire training set. And as I tried out models with different numbers for each of these hyperparameters, I evaluated each model using mean absolute error. So when the model predicted a day's average mobility, the difference was taken between the prediction and the actual value of that day's mobility. Then the absolute value is taken of all those differences, and the average of all those absolute values is the mean absolute error. So the lower the loss, which is the mean absolute error, the better the model's predictions. So when I ran this loop, I printed out at the bottom, you can see there, a list of all of the hyperparameters of that specific model, and the last item in the list is the loss of that model. So by the end of this loop, I had a bunch of those lists printed out, and I picked the model with the lowest loss and used those hyperparameters as the hyperparameters for my final model. So here are my hyperparameters for my final model. And on average, my prediction of the average mobility for a specific day was off by around 3.14%. And here's a graph that shows the loss getting smaller as it iterates through more epochs. So I have a screen recording video of my model being trained. And at the end, you can see that this time the model's error is around 3.17%. So right now it's starting to go through each epoch all the way up to 16, and the training loss is going down. And then at the end, you can see the 10 out of 10, that row is my loss on the testing set, which again was 3.17-ish%. And then lastly, I brought in some new data to see how well the model could predict it, because when training my model before, I only used data up to the last day of August. So here I used my neural network to predict the average mobility in Connecticut, where I live, for last Friday. And I'll show that. So for last Friday, the model predicted that Connecticut's average mobility would be about 15% below the baseline. And the true value for that average mobility is about 14.3% below the baseline. So the error or the loss for this prediction was about 0.7 or 0.73%. So some challenges I had when working on this project were combining the policy and mobility data sets in order to run the neural network, because they had vastly different numbers of data points per state per day. And the mobility data set also had data for specific regions within each state, which the policy data did not. And I ended up having to average out all the data for each state and its regions for each day in the mobility data in order to reduce it down to have the same amount of points as the policy data, and only then I could join the two data sets. Also, when doing the clustering and the neural network, the mobility data wasn't showing clear trends. So I had to go through the data to find out where there were some lurking variables. And eventually I realized I would have to take out the mobility data for parks, because the baseline was measured in January. But as the months got warmer, the increase in people as parks was not only due to coronavirus policies, but also to seasonal changes. And also the residential mobility data was measured in a different metric than the others, which led to complications when I was computing the average mobility. So I ended up having to take that out of my neural network as well. And lastly, a challenge was trying to train and test my network with only about 9,000 data points. Ideally, it would have been a little more than that, and that probably affected my loss a little bit. So some future extensions or next steps for this project would be using other machine learning models or other types of neural networks to predict the mobility from policy data. I could also expand to other countries, because both the Google dataset and the Oxford dataset did have data from other countries. And if I did that, I could compare US policy mobility to other countries and examine worldwide trends instead of just national trends. I could also include epidemiological data about the number of cases, and that would help analyze how that's related to policies and mobility. So that's the end of my presentation. Here are my sources. And if anyone has any questions, I'm happy to answer them.
All right, thanks, Tara. If anyone has any questions, feel free to unmute yourself and you can ask Tara whenever.
I guess for future models, are you thinking to possibly either predict more than one day out in the future, and then also what other machine learning algorithms would you use to compare against?
I think I would, if I had, especially with more data, definitely predicting more than one day in the future would be a cool thing to do. It was a little hard because I didn't have quite enough data that there were enough weeks of data points, I guess. But that's definitely something I would consider doing. And then if I were to use a different model, I guess the only other one I can think of that would work would be just a feed forward feed-forward neural network. And I guess that I would have to reformat my data a little bit so that it doesn't have to be, I guess, as related to time.
Cool. Yeah, I was wondering, is there any like maybe like SVM or any of the more like classical things that you would want to compare it to? Like not necessarily another neural network, but like maybe a more classical thing?
Yeah, I guess I don't know too many other machine learning models, but definitely I would be interested in learning more about those to try to use it with my data.
Cool.
Tara,
Hey, Tara. Or go ahead, Nick.
No, go ahead, Priscilla.
Amazing job, Tara, and you did a really good job presenting. I know you're so young, so like it must have been a little nerve-wracking, but you did a really good job.
Thank you.
So, and also, you know, that's like, it's really cool that you looked at time series data. I'm actually doing my project like to like look at those classical models that Greg is talking about, and it's a lot of material that we didn't really cover in our course. So like I'm curious in looking at this data set, because the thing about time series is like everybody wants to know like what factors are contributing to like the effects we're seeing. So I'm curious, what did you notice after working with these data sets about like those factors that are going in and what you think about how they're contributing to what you see at the end?
Yeah, so I think it was interesting to see how the mobility data didn't really correlate to the policy data as much as it, I guess, could have. Maybe that's like different states, cultures or whatever, but I also thought it was interesting how using the clusters from the mobility data and the policy data, I fed that into my data set, and that did increase accuracy by almost 1%. So it was cool to see that that data, I guess, like helped the neural network learn. I don't know if I answered your question.
Yeah, no, that you did. Yeah, and also in terms of like working with the time series model in such detail now, what was your experience of it compared to other types of neural networks that, you know, do images or something else? Because time series data is very different. So I'm curious, what was that like for you, and what did you learn about those time series data versus like other kinds of data?
Yeah, so I learned, I guess one big thing was having to reformat the whole data set, which I haven't had to do for other models, but that seemed like the best way to feed everything into my model. And then also, for me, at least in the data sets I used, it required a lot more cleaning to use, like data cleaning to use the time series data set, because I needed like specific amount of points for each day, and I need to make sure each day was there like in succession. And so those are just, I guess, like that's just my experience with this data, but that was what my experience with it. Yeah.
Those are things that are often, they get a lot of focus anytime you work with time series. So that is very accurate, that in terms of your takeaways from time series. I found a video where like actually someone who does stuff with biology like goes into working with time series data. You'd probably find it really interesting because it's like a 3-hour lecture on it. But yeah, I'll send it to you, because I think after this project you'll have a lot of like appreciation for the cleaning and all the different things that, you know, all the different thought that goes into that phase, because it's pretty extensive. I would definitely agree.
Wow, that's really cool. I'd be excited to see that.
Yeah, and congratulations and good luck on your on starting college.
Thank you.
You're welcome.
Hey, Tara. Yeah, I think the project and the presentation are very impressive. I wanted to ask, how long did it take to train the model, especially with those nested for loops? Because I imagine there's a lot of computational power that goes into it.
Yeah. So like once I had picked my hyperparameters, it was actually really quick to train the model, only like 20 seconds, but for the tuning the hyperparameters, that took probably like 4 or 5 hours, just because I used a lot of nested for loops and I went over a large range of hyperparameters. But running it in Google Colab on like their GPU or whatever, that definitely helped a lot.
Cool. And I guess one follow-up is, when you were cleaning and manipulating your data before feeding it through your model, did you use any of the K-means or principal component analysis to prepare the data, or was that just for demonstration purposes?
No, so I didn't use those for cleaning the data for the recurrent neural network, but the K-means and principal component analysis I did to use to put the data into the clusters. I used the cluster numbers of each state and I put that into my neural network. So I kind of indirectly used it.
All right, Tara, I have one more question for you that came up that I thought of during your demo that might be a little bit of a challenge, but I thought might be interesting. In light of the fact that you're using, mobility data, right, over the past certain amount of time, starting with some benchmark before COVID and then going through COVID to see kind of what people are up to. What sort of effect do you think, externalities like, for example, the wildfires on the West Coast, right, would have in your analysis and sort of the predictions that come out of it? And is there any way off the top of your head that you could think of to control for those? Just curious if you have any ideas there.
Yeah, so I didn't consider that as much. I did make graphs like month by month for the mobility data. So I could see that changing a little bit. And it was interesting. This isn't specifically with wildfires. I don't know the reason behind this, but as the pandemic has gone on, the mobility data is much less related to policies. I guess people are just like doing what they want now. But I think it would be interesting to see, like, to just use the states that have these wildfires as a problem, and just like watch their mobility data or like their mobility change throughout time with the wildfires, I guess. But I haven't done that.
It's completely fair. I was just curious. Obviously, it's hard to control for a huge mobility changing event like that, especially because it wasn't a thing when the data started, but just curious. Thanks for trying.
Yeah.
Awesome. Are there any more questions for Tara from the audience?
I have another question. So what kind of neural network problem-solving task is your favorite? And not even necessarily the one you did your project on, but just like having gone through the course and seen all the varieties of neural networks, like which one, do you have one that is like, wow, I love this one so much and it's like my favorite?
I really did like convolutional neural networks. I like how you can play around with the filtering and pooling and really tune it a lot to do exactly what you want. So I really liked that, but I thought there was like an interesting trade-off where convolutional neural networks take so much longer to train. And this recurrent neural network with even more data than some of the convolutional neural networks took like 1/8 of the time to train. So I like convolutional neural networks, but I don't like that they take a long time.
Awesome. Any other questions from the audience? If there are not, which it seems I gave enough time for, if there are not, Tara, you can end your screen share. Thank you so much for demoing today, for the effort you put into your project and the course. It was wonderful, at least for the little bit of time I got to teach you. I'm sure everyone else at Byte feels that way. Good luck next week and for the weeks that follow. Everyone else, there will be a recording link of this demo at some point. I will circulate that link as soon as it ends up in my email. Otherwise, thanks for joining everybody who showed up. Enjoy your weekends.
Thank you.